Unreasonable Effectiveness. In Chapter 1, I noted that the success of mathematics in physical theories has two aspects, one I call active and one passive. The active side reflects the fact that that scientists formulate the laws of nature in manifestly applicable mathematical terms. That is, they use mathematical entities, relations, and equations that were developed with an application in mind, often for the very topic under discussion. In those days, the researchers tend to rely on the perceived similarity between the properties of the mathematical concepts and the observed phenomena or experimental results. The effectiveness of mathematics may not appear to be so surprising in their cases, since one could argue that the theories were tailored to fit the observations. There is still, however, an astonishing part of the active use related to accuracy, which I will discuss later in this chapter. The passive effectiveness refers to cases in which entirely abstract mathematical theories had been developed with no intended application, only to metamorphose later into powerfully predictive physical models. No theory provides a spectacular example of the interplay between active and passive effectiveness. Notes. Notes are the stuff of that even legends are made of. You may recall the Greek legend of the guardian knot. An oracle decreed to the citizens of Phrygia that their next king would be the first man to enter the capital in an escort. Perdius, an unsuspecting peasant, what happened to get an escort into town that became king. Overwhelmed with gratitude, Gordius dedicated his wagon to the gods, and he tied it to a pole with an intricate knot that defied all attempts to untie it. A later prophecy pronounced that the person to untie the knot would become king of Asia. As fate would have it, the man who eventually untied the knot in the year 333 BC was Alexander the Great. The, was Alexander the Great, and he indeed subsequently became ruler of Asia. Alexander's solution to the Gordian knot, however, was not exactly one we would call subtle or even fair. He apparently sliced through the knot with his sword. But we don't have to go all the way back to ancient Greece to encounter knots. A child drying his shoelaces, a girl bathing her hair, a grandma knitting a sweater, or a sailor mooring a boat are all using knots of some sort. Various knots were even given imaginative names such as fisherman's bend, enlistman's tie, cat's paw, two lover's knot, granny, and hangman's knot. Maritime knots, in particular, were historically considered sufficiently important to have inspired an entire collection of books about them in 17th century England. One of these books, incidentally, was written by none other than English adventurer John Smith, 1580 until 1631, better known for his romantic relationship with the Native American princess Pocahontas. The mathematical theory of knots was born in 1771 in a paper written by the French mathematician Alexandre Théophile van der Monde, 1735 until 96. Van der Monde was the first to recognize that knot could be studied as part of the subject of geometry of position, which deals with relations depending on position alone, ignoring sizes and calculation with quantities. Next in line in terms of his role in the development of knot theory was the German prince of mathematicians was the German prince of mathematics Carl Friedrich Gauss. Several of Gauss' notes contain drawings and detailed descriptions of knots, along with some analytic explanations of their properties. As important as the works of Van der Monde Gauss and a few other 19th century mathematicians work. However, the main driving force between the modern mathematical knot theory came from an unexpected source, an attempt to explain the state of matter. The idea originated in the mind of the famous English physicist William Thomson, better known today as Lord Kelvin, 1824 until 1907. Thomson's effort concentrated on formulating a theory of atoms, the basic building blocks of matter. According to his truly imaginative conjecture, atoms were really noted tubes of ether, that mysterious substance that was supposed to permeate all space. The variety of chemical elements could, in the context of this model, be accounted for the rich diversity of knots. If Thomson's speculations sounds almost crazy today, it's only because we have had an entire century to get used to and test experimentally the correct model of the atom, in which electrons orbit the atomic nucleus. But this was England of the 1860s, and Thomson was deeply impressed with the stability of complex smoke rings and their ability to vibrate, to properties considered essential for modeling atoms at the time. In order to develop the knot equivalent of a periodic table of the elements, Thomson had to be able to classify dots, find out which different knots are possible, and it was this need for knot tabulation that sparked a serious interest in the mathematics of knots. As I explained already in chapter 1, a mathematical knot looks like a familiar knot in a string, only with the strings and spliced. In other words, a mathematical knot is protected by a closed circle with no loose ends. A few examples are presented in figure 54, when the three-dimensional knots are represented by the projections of shadows in the plane. The position in space of any two strands that cross each other is indicated by in the figure interrupting the line that depicts the lower strand. The simplest knot, the one called the unknot, is just a closed circular curve as in figure 54a. The trefoil knots found in figure 54b has three crossings of the strands, and the figure 54c has four crossings. In Thomson's theory, these three knots could, in principle, be models of three atoms of increasing complexity, such as the hydrogen, carbon, and oxygen atoms, respectively. Still, a complete knot classification was badly needed, and the person who set out to sort the knots was Thomson's friend, the Scottish mathematical physicist Peter Gittray, 1831 until 1901. The types of questions mathematicians ask about knots are really not very different from those might about ask an ordinary knotted string or tangled ball of yarn. Is it really knotted? Is one knot equivalent to another? What the latter question means is simply, can one of the form with into the shape of the other without breaking the strands or pushing one strand to the other like a magician's linking rings. The importance of this question is demonstrated in figure 55, which shows that by certain manipulations one can obtain two very different representations of what is actually the same knot. Ultimately, knot theory searches for some precise way of proving that certain knots, such as the trefoil knot and the figure 8 knot, figure 54b and figure 44c, are really different, while ignoring the superficial differences of other knots, such as the two knots in figure 55. T started his classification worked the hard way, without any rigorous mathematical principle to guide him. He compiled lists of curves with one crossing two crossings, three crossings, and so on, in collaboration with the Reverend Thomas Pennington Kirkman, 1806 until 95, who was also an amateur mathematician. Here is a shifting through the curves to eliminate duplications by equivalent nodes. This was not a trivial task. You must realize that at every crossing there are two ways to choose which strand would be uppermost. This means that if a curve constraints says 7 crossing, there are 128 nodes to consider. In other words, human life is too short to complete in this intuitive way the classification of nodes with tens of crossings or more. Nevertheless, Tate's labor did not go unappreciated. The great James Clerk Maxwell, who formulated the classical theory of electricity and magnetism, treated Thomson's atomic theory with respect, stating that it satisfies more of the conditions that any atom hitherto considered, being at the same time well aware of Tate's contribution. Maxwell offered the following rhyme: clear your coil or kinkings into perfect plating, locking loops and linkings interpenetrating. By 1877, Tate had classified alternating nodes with up to 7 crossings. Alternating nodes are those in which the crossings go alternately over and under, like the thread in the woven carpet. Tate also made a few more pragmatic discoveries in the form of basic principles that were later Christian Tate's conjectures. These conjectures were so substantial, by the way, that they resisted all attempts to prove them rigorously until the late 1980s. In 1885, in 1885, Tate published tables of knots with up to 10 crossings, and he decided to stop there independently. University of Nebraska professor Charles Newton Little, 1858 until 1920, also published in 1899 tables of alternating knots with 10 or fewer crossings. Lord Kelvin always thought fondly of Tate. At a ceremony at Peterhouse College in Cambridge, where a portrait of Tate was presented, Lord Kelvin said, "I remember Tate was remarking that nothing but science is worth living for." It was sincerely said, but Tate himself proved it to be not true. Tate was a great reader. He would get Shakespeare, Dickens, and Thackeray off by heart. His memory was wonderful. When he was read sympathetically, he ever after remembered. Unfortunately, by the time Tate and Little completed their hairy work on knot tabulation, Kelvin's theory had already been totally discarded as a potential atomic theory. Still, interest in knots continued for its own sake, the difference being that, as the mathematician Michael Atiyah has put it, the study of knots became an esoteric branch of pure mathematics. The general area of mathematics where qualities such as size, smoothness, and in some sense even shape are ignored is called topology. Topology, the rubber sheet geometry, examines those properties that remain unchanged when space is stretched or deformed in any fashion, without tearing off pieces or poking holes. By their very nature, knots belong in topology. Incidentally, mathematicians distinguish between knots, which are single knotted loops, links, which are sets of knotted loops are tangled together, and braids, which are sets of vertical strings attached to a horizontal bar at the top and bottom ends. You were not impressed with the difficulty of classifying knots. Consider the following very telling fact. Charles Little's table, published in 1899, after 6 years of work, contained 43 non-alternating nodes of 10 crossings. This table was questioned by many mathematicians and believed to be correct for 75 years. Then in 1974, the New York lawyer and mathematician Kenneth Berko was experimenting with ropes on his living room floor. To his surprise, he discovered that two of the nodes in Litto's table were in fact the same. We now believe that there are 42 distinct non-alternating nodes of 10 crossings. While the 20th century witnessed great strides in topology, progress in knot theory was relatively slow. One of the key goals of the mathematicians studying knots has been to identify properties that tool distinguish knots. Such properties are called invariants of knots. They represent quantities for which any two different projections of the same knot yield precisely the same value. In other words, an ideal invariant is literally a fingerprint of the knot, a characteristic property of the knot that does not change by deformations of the knot. Perhaps the simplest invariant one can think of is the minimum number of crossings in a drawing of the knot. For instance, no matter how hard you try to disentangle the 12-hole knot, figure 54b, will never reduce the number of crossings to fewer than 3. Unfortunately, there are a number of reasons why the minimal number of crossings is not the most useful invariant. First, as figure 55 demonstrates, it is not always easy to determine whether a knot has been drawn with the minimum number of crossings. Second, more important, many knots that are actually different have the same number of crossings. In figure 54, for instance, there are 3 different knots with 6 crossings, and no fewer than 7 different knots with 7 crossings. The minimum number of crossings therefore does not distinguish most knots. Finally, the minimum number of crossings by its very simplistic nature does not provide much insight into the properties of knots in general. A breakthrough in knot theory came in 1928 when the American mathematician James Weather Alexander 1880 until 1971 discovered an important invariant that has become known as the Alexander polynomial. Basically, the Alexander polynomial is an algebraic expression that uses the arrangement of crossings to label the knot. The good news was that if two knots are different Alexander polynomials, then the knots were definitely different. The bad news was that two knots that had the same polynomial could still be different knots. While extremely helpful, therefore, the Alexander polynomial was still not perfect for distinguishing knots. Mathematicians spent the next 4 decades exploring the conceptual basis for the Alexander polynomial and gaining further insights into the properties of knots. Why were they getting so deep into the subject? Certainly not for any practical application. Thomson's atomic model had long been forgotten, and there was no other problem in the sciences, economics, architecture, or any other discipline that appeared to require theory of knots. Mathematicians were spending endless hours on knots simply because they were curious. To these individuals, the idea of understanding knots and the principles that govern them was exquisitely beautiful. The sudden flash of insight afforded by the Alexander polynomial was irresistible to mathematicians, as the challenge of climbing Mount Everest was to George Mallory, who famously replied because it is there, to the question of why he wanted to climb the mountain. In the late 1960s, the prolific English-American mathematician John Horton Conway discovered the procedure for unknotting knots gradually, thereby revealing the underlying relationship between knots and their Alexander polynomials. In particular, Conway introduced the simple surgical questions that could serve as the basis for defining a knot invariant. Conway or converse operations, dab, flip, and smoothing are described schematically in Figure 56. In the flip, Figure 56a, the crossing is transformed by running the upper strand under the lower one. The figure also indicates how one might achieve this transformation in a real knot in a string. Note that the flip obviously changes the nature of the knot. For instance, you can easily convince yourself that a truffle knot in Figure 54b will become the unknot Figure 54a following a flip. Converse smoothing operation eliminates the crossing altogether. Figure 56b by reattaching the strands the wrong way. Even with the understanding gained from Conway's work, mathematicians remain convinced for almost 2 more decades that no other invariants for the type of the Alexander polynomial could be found. The situation changed dramatically in 1984. The New Zealander-American mathematician Vaughan Jones was not studying knots at all. Rather, he was exploring an even more abstract world of the mathematical entities known as von Neumann algebras. Unexpectedly, Jones noticed that a relation that resurfaced in von Neumann algebras looks suspiciously similar to a relation in knot theory, and he met with Columbia University knot theorist John Bigman to discuss possible applications. An examination of the relation eventually revealed an entirely new invariant for knots dubbed the Jones polynomial. The Jones polynomial was immediately recognized as a more sensitive invariant than the Alexander polynomial. It distinguishes, for instance, between knots and their minor images, e.g., the right-handed and left-handed tripole knots in Figure 57, for which the Alexander polynomials were identical. More importantly, however, Jones' discovery generated an unprecedented excitement among knot theorists. The announcement of a new invariant triggered such a flurry of activity that the world of knots suddenly resembled the stock exchange floor on a day on which the Federal Reserve unexpectedly lowers interest rates. There was much more to Jones' discovery than just progress in knot theory. The Jones polynomials suddenly connected to a bewildering variety of areas in mathematics and physics, ranging, ranging from statistical mechanics used, for instance, to study the behavior of large collections of atoms or molecules, to quantum groups, a branch of mathematics related to the physics of the subatomic world. Mathematicians all over the world immerse themselves feverishly in attempts to look for even more general invariants that would somehow encompass both the Alexander and Jones polynomials. This mathematical race ended up in what is perhaps the most astonishing result in the history of scientific competition. Only a few months after Jones revealed his new polynomial, four groups working independently and using three different mathematical approaches announced at the same time the discovery of an even more sensitive invariant. The new polynomial became known as the Humphrey polynomial after the first letters in the names of the discoverers Schuster, Ognianu, Millet, Wright, Licorice, and Jeter. Furthermore, as if a group crossing the finish line in a dead heat weren't enough, two Polish mathematicians, Brzezinski and Tass, discovered independently precisely the same polynomial, but they missed the publication date due to capricious mail system. Consequently, the polynomial is also referred to as the home field, also so polynomial, adding to the first letters in the names of the Polish discoverers. Since then, while other invariants have been discovered, a complete classification of knots remains elusive. The case of precisely which knot can be twisted and turned to produce another knot without the use of scissors is still unanswered. The most advanced invariant discovered to date is the work of the Russian-French mathematician Maxim Konstantinovich, who received the prestigious Blitz Medal in 1998 and the Crafoord Prize in 2008 for his work. Incidentally, in 1998, Jim Schuster of Pitzer College in Claremont, California, and Jeffrey Weeks of Canton, New York, tabulated all the noted loops have insisted of fewer crossings. An identical tabulation was produced independently by Morgan Tistowati of the University of Tennessee in Knoxville. Each list contains precisely 1,701,938 different notes. The real surprise, however, came not so much from the progress in knot theory itself, but from the dramatic and unexpected comeback that knot theory has made in a wide range of sciences. Life. Recall that knot theory was motivated by a wrong model of the atom. Once that model died, however, mathematicians were not discouraged. On the contrary, they embarked with great enthusiasm on a long and difficult journey of trying to understand knots in their own right. Imagine then their delight while knot theory suddenly turned out to be the key to understanding fundamental processes involving the molecules of life. Do you need any better example of the passive role of pure mathematics in explaining nature? Deoxyribonucleic acid, or DNA, is the genetic material of all cells. It consists of two very long strands that are intertwined and twisted around each other millions of times to form a double helix. Along the two backbones, which can be thought of as the sides of ladder, sugar and phosphate molecule alternate. The rungs of the ladder consist of pairs of bases contacted by hydrogen bonds in the prescribed fashion, adenine bonds only with thymine, and cytosine only with guanine. Figure 58. When the cell divides, the first step is replication of DNA so that daughter cells can receive copies. Similarly, in the process of transcription, in which genetic information from DNA is copied to RNA, a section of the DNA double helix is uncoiled and only one DNA strand serves as a template. After the synthesis of RNA is complete, the DNA recoils into its helix. Neither the replication nor the transcription process is easy, however, because DNA is so tightly knotted and coiled in order to compact the information storage that unless some unpacking takes place, these vital life processes could not proceed smoothly. In addition, for the replication process to reach completion, offspring DNA molecules must be unknotted, and the parent DNA must eventually be restored to its original configuration. The agents that take care of the unknotting and disentanglement are enzymes. Enzymes can pass one DNA strand to another by creating temporal breaks and reconnecting the ends differently. Does this process sound familiar? These are precisely the surgical operations introduced by Conway for the unraveling of mathematical knots represented in Figure 56. In other words, from a topological standpoint, DNA is a complex knot that has to be unknotted by enzymes to allow for replication or transcription to occur. By using knot theory to calculate how difficult it is to unknot the DNA, researchers can study the properties of the enzymes that do the unknotting better at using experimental visualization techniques such as electron microscopy and gel electrophoresis. Scientists can actually observe and quantify the changes in the knotting and linking of DNA caused by an enzyme. Figure 59 shows an electron micrograph of adenine knot. The challenge to a mathematician is then to deduce the mechanisms by which the enzymes operate from the observed changes in the topology of DNA as a byproduct. The changes in the numbering of crossings in the DNA do not give biologists a measure of the reaction rates of the enzymes. How many crossings per minute can an enzyme of a given concentration affect? But molecular biology is not the only arena in which knot theory found unforeseen applications. String theory, the current attempt to formulate a unified theory that explains all the forces in nature, is also concerned with knots. D is the force that operates on the larger scales. It holds the stars in the galaxies together and influences the expansion of the universe. Einstein's general relativity is a remarkable theory of gravity. Deep within the atomic nucleus, other forces in a different theory reigns supreme. The strong nuclear force holds particles called quarks together to form the family of protons and neutrons, the basic constituents of matter. The behavior of the particles and the forces in the subatomic world is governed by the laws of quantum mechanics. Two quarks and galaxies play by the same rules. Physicists believe they should, even though they don't yet quite know why. For decades, physicists have been searching for a theory of everything, a comprehensive description of the laws of nature. In particular, they want to bridge the gap between the large and the small with a quantum theory of gravity, a reconciliation of general theory with quantum mechanics. String theory appears to be the current best bet for such a theory of everything. Originally developed and discarded as a theory for the nuclear force itself, string theory was revived from obscurity in 1974 for the nuclear force itself. String theory was revived from obscurity in 1974 by physicists John Schwarz and George Sack. The basic idea of string theory is quite simple. The theory proposes the elementary subatomic particles, such as electrons and quarks, are not point-like entities with no structure. Rather, the elementary particles represent different modes of vibration of the same basic string. The cosmos, according to these ideas, is filled with tiny, flexible rubber band-like loops, just as a violin string can be plucked to produce different harmonies. Different vibrations of these looping strings correspond to distinct matter particles. In other words, the world is something like a symphony. Since strings are closed loops moving through space, as time progresses, they sweep areas known as worldsheets in the form of cylinders as in figure 60. In a string amidst of other strings, this cylinder forks to form these bone-shaped structures. When many strings interact, they form an intricate network to fuse the nut-like cells. While studying these types of complex topological structures, string theorists Hiroshi Oguri and Kumrun Fava discovered a surprising connection between the number of donut cells, the intrinsic geometric properties of knots, and the Jones polynomial. Even earlier, at Witten, one of the key players in string theory, created an unexpected relation between the Jones polynomial and the very foundation of string theory, known as quantum field theory. Witten's model was later rethought from a purely mathematical perspective by the mathematician Michael Atiyah. So string theory and knot theory live in perfect symbiosis. On one hand, string theory has benefited from research in knot theory. On the other, string theory has actually led to the insights in knot theory with much broader scope. The string theory searches for explanations for the most basic constituents of matter, much in the same way that Thomson originally searched for a theory of atoms. Thomson mistakenly thought that knots could provide the answer. By a surprising twist, string theorists find that knots can indeed provide at least some answers. The story of knot theory demonstrates beautifully the unexpected powers of mathematics. As I have mentioned earlier, even the active side of the effectiveness of mathematics alone, when scientists generate the mathematics they need to describe observable science, presents some baffling surprises when it comes to accuracy. Let me describe briefly one topic in physics in which both the active and the passive aspects play a role, but which is particularly remarkable because of the obtained accuracy. A weighty accuracy. Newton took the laws of falling bodies discovered by Galileo and other Italian experimentalists, combined them with the laws of planetary motion determined by Kepler, and used this unified scheme to put forth a universal mathematical law of gravitation. Along the way, Newton had to formulate an entire new branch of mathematics, calculus, that allowed him to capture concisely and coherently all the properties of his proposed laws of motion and gravitation. The accuracy to which Newton himself could verify his law of gravity, even the experimental and observational results of his day, was no better than about 4%. Yet the law proved to be accurate beyond all reasonable expectations. By the 1950s, the experimental accuracy was better than one ten thousandth of a percent. But this is not all. A few recent speculative theories aim at explaining the fact that the expansion of our universe seems to be speeding up, suggested that gravity may change its behavior on very small distance scales. Recall that Newton's law states that the gravitational attraction decreases as the inverse square of the distance. That is, if you double the distance between two masses, the gravitational force each mass feels becomes 4 times weaker. The new scenarios predicted deviations from this behavior at distances smaller than 1 millimeter, the 25th part of an inch. Eric Adelberger, Daniel Kapner, and their collaborators at the University of Washington, Seattle, conducted a series of ingenious experiments to test this predicted change in the dependence on the separation. Their most recent results, published in January 2007, show that the inverse square law holds down to a distance of 56 thousandths of a millimeter. So a mathematical law that was proposed more than 300 years ago on the basis of very scientific observations not only turned out to be phenomenally accurate, but also proved to hold in a range that couldn't even be probed until very recently. There was one major question that Newton left completely unanswered. How does gravity really work? How does the Earth, a 250,000 miles away from the Moon, affect the Moon's motion? Newton was aware of this deficiency in his theory, and he openly admitted it in the Principia. Hitherto we have explained the phenomena of the heavens and of our sea by the power of gravity, but have not yet assigned the cause of this power. This is certain that it must proceed from a cause that penetrates to the very centers of the sun and planets, and propagates its feature on all sides to immense distances, decreasing always as the inverse square of the distances. But hitherto I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypothesis. The person who decided to meet the challenge posed by Newton's omission was Albert Einstein, 1879 until 1955. In 1907, in particular, Einstein had a very strong reason to be interested in gravity. His new theory of special relativity appeared to be in direct conflict with Newton's law of gravitation. Newton believed that gravity's action was instantaneous. He assumed that it took no time at all for planets to feel the sun's gravitational force or for an apple to feel the Earth's attraction. On the other hand, the central pillar of Einstein's special relativity was the statement that no object, energy, or information could travel faster than the speed of light. So how could gravity work instantaneously? As the following example we show, the consequence of this contradiction could be disastrous to concepts as fundamental as our perception of cause and effect. Imagine Imagine that the sun were to somehow suddenly disappear. Robbed of the force holding it to its orbit, the Earth would, according to Newton, immediately start moving along a straight line apart from a small deviations due to the gravity of the other planets. However, the sun would actually disappear from view to the Earth's inhabitants only about 8 minutes later. Since this is the time it takes light to traverse the distance from the sun to the earth, in other words, the change in the earth's motion will precede the sun's disappearance. To remove this conflict and at the same time to tackle Newton's unanswered question, Einstein engaged almost obsessively in a search for a new theory of gravity. This was a formidable ask. Any new theory had not only to preserve all the remarkable successes of Newton's theory, but also to explain how gravity works, and to do so in a way that is compatible with special relativity. After a number of false starts and long wanderings down blind alleys, Einstein finally reached this goal in 1915. His theory of general relativity is generally regarded by many as one of the most beautiful theories even formulated. The heart of Einstein's groundbreaking insight lay the idea that gravity is nothing but warps in the fabric of space and time. According to Einstein, just as golf balls are guided by their warps and curves across an undulating green, planets follow curved paths in their warp space representing the sun's gravity. In other words, in the absence of matter or other forms of energy, space-time, the unified fabric of the three dimensions of space and one of time, would be flat. Matter and energy warp space-time just as a heavy bowling ball causes a trampoline to sag. Planets follow the most direct path in this curved geometry, which is a manifestation of gravity. By solving the how it works problem for gravity, Einstein also provided a framework for addressing the question of how fast it propagates. The latter question boiled down to determining how fast waves in space-time and could travel. This was a bit like calculating the speed of rivers in a pond. Einstein was able to show that in general relativity, gravity traveled precisely at the speed of light, which eliminated the discrepancy that existed between Newton's theory and special relativity. If the sun were to disappear, the change in the Earth's orbit would occur 8 minutes later, coinciding with our observing the disappearance. The fact that Einstein had turned web four-dimensional spacetime into the cornerstone of his new theory of the cosmos meant that he badly needed a mathematical theory of such geometrical entities. In desperation, he turned to his old classmate, the mathematician Marcel Grossman, 1878 until 1936. I have become imbued with great respect for mathematics, the most subtle parts of which I had previously regarded as sheer luxury. Grossman pointed out that Riemann's non-Euclidean geometry, described in Chapter 6, was precisely the tool that Einstein needed, a geometry of curved spaces in a number of dimensions. This was an incredible demonstration of what I dubbed the perceived effectiveness of mathematics, which Einstein was quick to acknowledge. We may in fact regard geometry as the most ancient branch of physics, he declared. Without it, I would have been unable to formulate the theory of relativity. General relativity has also been tested with impressive accuracy. These tests are not easy to come by, since the curvature in spacetime introduced by objects such as the sun is measured only in parts per million, while the original tests were all associated with observations within the solar system, e.g., tiny changes to the orbit of the planet Mercury as compared to the predictions of Newtonian gravity. More exotic tests have recently become feasible. One of the best verifications uses an astronomical object known as a double pulsar. A pulsar is an extraordinarily compact radio wave emitting star with a mass somewhat larger than the mass of the Sun, but a radius of only about 6 miles. The density of such a star, known as a neutron star, is so high that 1 cubic inch of its matter has a mass of about a billion tons. Many of these neutron stars spin very fast while emitting radio waves for their magnetic poles. When the magnetic axis is somewhat inclined to the rotation axis, as in figure 61, the radio beam from a given pole may cross our line of sight only once every rotation, like the flash of light from a lighthouse. In this case, the radio emission will appear to be pulsed, hence the name pulsar. In one case, the pulsars revolve around the mutual center of gravity in a closed orbit, creating a double pulsar system. There are two properties that make this double pulsar an excellent laboratory for testing general relativity. Radio pulsar Radio pulsars are superb clocks. Their rotation rates are so stable that, in fact, they surpass atomic clocks in accuracy. And two pulsars are so compact that their gravitational fields are very strong, producing significant relativistic effects. These features allow astronomers to measure very precisely changes in the light travel from the pulsar to Earth caused by the orbital motion of the two pulsars in each other's gravitational field. The most recent test was the result of precise timing observations taken over a period of 2.5 years on the double pulsar system known as BSR G0737 3039AB. The long telephone number reflects the coordinates of the system in the sky. The two pulsars in the system complete an orbital revolution in just 2 hours and 27 minutes, and the system is about 2000 light years away from Earth. A light year is the distance light travels in 1 year in a vacuum, about 6 trillion miles. A team of astronomers led by Michael Kramer of the University of Manchester measured the relativistic correlations to the Newtonian motion. The results, published in October 2006, agree with the value predicted by general relativity within an uncertainty of 0.05%. Incidentally, both special relativity and general relativity play an important role in the global positioning system GPS that helps us find our location on the surface of the Earth and our way from place to place, whether in a car, airplane, or on foot. The GPS determines the current position of the receiver by measuring the time it takes the signal from several satellites to reach it, and by that calculating on the known positions of each satellite. Special relativity predicts that the atomic clocks on board the satellites should tick more slowly, falling behind a few millionths of a second per day than those of the ground because of the relativity motion. At the same time, general relativity predicts that the satellite clocks should tick faster were few tens of millions of a second per day than those of the ground due to the fact that high above the Earth's surface the curvature in space-time resulting from the Earth's mass is smaller. Without making the necessary correlation of these two effects, error in global positions could accumulate at a rate of more than 5 miles in each day. The theory of gravity is only one of the many examples that illustrate the miraculous suitability and astonishing accuracy of the mathematical formulation of the laws of nature. In this case, as in numerous others, what we got out of the equations was much more than what was originally put in. The accuracy of both Newton's and Einstein's theories proved to far exceed the accuracy of the observations that the theories attempted to explain in the first place. Perhaps the best example of astonishing accuracy that a mathematical theory can achieve is provided by quantum electrodynamics theory. The theory describes all phenomena involving electricity, charged particles, and light. In 2006, a group of physicists at Harvard University determined the magnetic moment of the electron, which measures how strongly the electron interacts with a magnetic field to a precision of 8 parts in a trillion. This is an incredible experimental feat in its own right, but when you add to that the fact that the most recent theoretical calculations based on KED reach a similar precision, and that the two results there, the accuracy becomes almost unbelievable. When he heard about the continuing success of KED, one of KED's originators, the physicist Freeman Dyson, reacted. I am amazed at how precisely nature dances to the tune, we scribbled so carelessly 57 years ago, and at how the experimenters and the theorists can measure and calculate fragments to a part in a trillion. But accuracy is not the only claim to fame of mathematical theories. Predictive power is another. Let me give just two simple examples of one for let me give just two simple examples, one from the 19th century and one from the 20th century, that demonstrate this potency. The former theory predicted a new phenomenon and the later the existence of new fundamental particles. James Clerk Maxwell, who formulated the classical theory of electromagnetism, showed in 1864 that the theory predicted the varying electric or magnetic fields should generate propagating waves. These waves, the familiar electromagnetic waves, e.g. radio, were first detected by the German physicist Heinrich Hertz, 1857-1994, in a series of experiments conducted in the late 1880s. In the later 1860s, physicists Stephen Weinberg, Sheldon Glashow, and Abdus Salam developed a theory that treats the electromagnetic force and weak nuclear force in a unified manner. This theory, now known as the electroweak theory, predicted the existence of two particles called W and Z bosons that had never before been observed. The particles were ambiguously detected in 1983 in accelerator experiments, which meshed one subatomic particle into another at very high energies, led by physicists Carlo Rubbia and Simon van der Meer. The physicist Eugene Wigner, who coined the phrase the unreasonable effectiveness of mathematics, proposed to call all of these unexpected achievements of mathematical theories the empirical law of epistemology. Epistemology is the discipline that investigates the origin and limits of knowledge. If this law were not corrected, he argued, scientists would have lacked the encouragement and reassurance that are absolutely necessary for a thorough exploration of the law of nature. Wigner, however, did not offer any explanation for the empirical law of epistemology, rather regarded it as a wonderful gift, for which we should be grateful even though we do not understand its origin. The lead winner this gift captured the sense of the question about the unreasonable effectiveness of mathematics. At this point, I believe that we have gathered enough clues that we should at least be able to transcend the cases we started with. Why is mathematics so effective and productive in explaining the world around us that it even yields new knowledge? And is mathematics ultimately invented or discovered?